Namaste, dear students. I, Dr.Mrs P.S.Joshi, working as Assistant Professor in General Engineering Department from Walchand Institute of Technology. I welcome you all to this video lecture of optical fiber. In this lecture, today we are going to study in detail about the important term related with optical fiber, that is acceptance angle. So, by the end of this lecture, students will be able to define and calculate acceptance angle of an optical fiber. These are the contents of the session. So, the main function of an optical fiber is to accept and transmit as much light from the source as possible, and the light propagates from one end of the fiber to the other end through total internal reflection. So this light gathering ability of the fiber depends on two factors, that is core size and numerical aperture. The numerical aperture, it is again dependent on two factors, that is acceptance angle and the fractional refractive index change. So the larger the core size, the more light will be accepted by the fiber, and this numerical aperture, this term is new to us. So first students, we will start from acceptance angle. We will see what is acceptance angle. Before starting acceptance angle, we will revise a few points regarding critical angle. Students, in the last video we have seen in detail about this critical angle. So for this, let us again consider a step index fiber into which the light is launched at one end. The end at which light enters the fiber is called as launching end. Let the medium through which light enters the fiber is air. So in this step index fiber, the refractive index of core is N1 and that of cladding is N2. For total internal reflection to occur, core index is greater than cladding index. So we will here consider two rays entering in the fiber at two different angles of incidence. Let us go for the first case. The ray is incident at an angle theta 2 with respect to the axis of the fiber. This ray undergoes refraction at point A on the interface between air and the core. The ray refracts into the fiber at an angle theta 1, where this theta 1 is less than theta 2. Now the ray reaches the core cladding interface at point D. At this point D, the refraction takes place again and the ray travels in the cladding. Finally, at point E, the ray refracts once again and emerges out of the fiber, that is into the air. Students, what does this mean? Are you getting? Yes, it means that the ray does not propagate through the fiber. Let us next consider the another ray. The ray incident at an angle theta undergoes refraction at point A on the interface and propagates at an angle theta c in the fiber. At point B on the core cladding interface, the ray undergoes total internal reflection as core index is greater than cladding index. Let us assume that the angle of incidence at the core cladding interface is the critical angle phi c, where phi c is given by sine inverse n2 upon n1. So here we can compare both the rays. A ray incident with an angle larger than phi c will be confined to the core and propagate in the fiber. A ray incident at the core cladding interface at the critical angle is called critical ray. The critical ray makes an angle phi c with the axis of the fiber. It is obvious that the rays with propagation angles larger than theta c will not propagate in the fiber. Therefore, the angle theta c is called the critical propagation angle. Thus, only those rays which are refracted into the cable at angles theta r less than theta c will propagate in the optical fiber. Now let us see what acceptance angle is. For this, again we will consider a step index fiber into which the light is launched at one end. Let N0 be the refractive index of medium through which light enters the fiber. Let refractive index of core and cladding be N1 and N2 respectively. Students, again to occur total internal reflection, N1 is always greater than N2. Assume that a ray of light enters the fiber at an angle theta I to the axis of the fiber. The ray refracts at an angle theta r and strikes the core cladding interface at an angle phi. If this striking angle is greater than critical angle phi c, then the ray undergoes total internal reflection at the interface, since N1 is greater than N2. As long as the angle phi is greater than phi c, the light will stay within the fiber. Let us now apply Snell's law to the launching phase of the fiber. We get the equation as sin theta I divided by sin theta r is equal to N1 upon N0. Now here we have to find out acceptance angle, that is the maximum angle through which the light will be accepted by the fiber. So students, if we increase theta I, then what will happen? Will it affect on angle of refraction? Yes, the angle of refraction theta r will also increase. And will it affect on striking angle? Yes, obviously the striking angle will decrease. Yes students, you are right. If we increase theta I beyond a limit, striking angle phi will drop below phi c and the ray escapes from the side walls of the fiber. So, the largest value of theta I occurs when phi is equal to phi c. Dear students, please note this correctly, that the largest value of theta I occurs when phi is equal to phi c. Now let us move to the next steps. From triangle ABC, from figure we can see that this sin theta r, it is equal to sin 90 minus phi. So which can be also written as cos phi. From equations 1 and 2, we can write down the equation as sin theta I is equal to N1 upon N0 into cos phi. When phi is equal to phi c, then theta I will be equal to theta I maximum. So students, in the previous equation, now we will replace phi by phi c, then theta I will be equal to theta I maximum. Therefore, the equation will become as sin theta I maximum is equal to N1 upon N0 into cos phi c. Now we have to find out the value of cos phi c. From the definition of critical angle, we have the equation as sin phi c is equal to N2 upon N1. So, further simplifying the equation, we will get the equation for cos phi c as under root N1 square minus N2 square upon N1. Now, from equations 4 and 5, we will get it as sin theta I maximum is equal to N1 upon N0 multiplied by under root N1 square minus N2 square divided by N1. N1 gets cancelled. So, the equation becomes as sin theta I maximum is equal to under root N1 square minus N2 square divided by N0. Quite often, the incident ray is launched from air medium, for which a refractive index is equal to 1. And let us replace theta I maximum is equal to theta 0. Therefore, the equation for theta 0 is equal to sin inverse under root N1 square minus N2 square. The angle theta 0 is called the acceptance angle of the fiber. So, we can define acceptance angle as acceptance angle is the maximum angle that a light ray can have relative to the axis of the fiber and propagates down the fiber. Thus, only those rays which are incident on the face of the fiber making angles less than theta 0 will undergo repeated total internal reflections and reach the other end of the fiber. Obviously, larger acceptance angle makes it easier to launch light into the fiber. These are the references for this lecture. Thank you.